Okay, so the Laser Houston team, it's small, but it's growing. We are the chairs here, Serpic Angelini and me, Ison Caro Chassin. And our technical director is hiding in the corner back there, Carlos Pelayo Martinez. And technical support is Gabi Ozuna, who signed you in at the door. Probably followed you around a bit. And Nicholas Stewart Spencer, who helped us print all the flyers. Thank you. So without further ado, the speakers of tonight, we will have first Dr. Rafael Verduzco. He's an associate professor of chemical and biomolecular engineering at Rice University, and he is talking about plastic fantastic, and I am so excited to hear his talk. And we also will have Geraldine Weiss, who's an artist, and she will be presenting her work with an emphasis on the project, the Brain Painting, and the Nahual project, which is a collaboration with other neuroscience professors at University of Houston. So thank you very much, and are you ready? Feel free to ask questions. We will have a Q&A after each presentation.
Great. Well, thanks for the introduction. Thank you for putting together this event. You know, for a long time I've thought that I should really kind of reach out more to artists and learn more about the artistic side. And so I'm excited about this event. I'm happy to be here. Definitely interested to learn today. So I'm going to tell you about some of the work in my lab. My lab does work with soft materials. Everything we do involves polymers. And so, you know, if you think about what are polymers, well, polymers are basically in anything plastic around us. But polymers can do a lot more cool things than just containers and, you know, boxes and tabletops and things like that. And that's what I'm going to talk about today, some of the fantastic things that plastics or polymers can do. And there's 3 parts to my talk. I don't know if I'll get to do all of them because I don't want to go on too long. As I was putting this together, once I hit 40 slides, I said, okay, that's probably enough. So I'll try to get through them quickly. But yes, if you have any questions, please feel free to interrupt. And yes, all the work I do, you know, is really, you know, done by not just me. There's a whole team of graduate students and undergrads at Rice, right? So, you know, so I get to throw out ideas, and then they bring me these fantastic materials and results, and I say, oh, well, why don't you try this? And then they do it and bring some more fantastic results. And so, you know, I do want to acknowledge them at the beginning. You know, another reason I entitled my talk Plastic Fantastic is really I stole it from a book. I like the title, but this book is actually about one of the most notorious scientific frauds that has ever been committed. It's a really good book. But my work isn't fraudulent, right? So the talk I'm going to give has nothing to do with the content of this. I just like the title, Plastic Fantastic. But if you are interested in this story, I do encourage you to read it. Just about well, it is about a real story that happened in science 15, 20 years ago. Okay, so the first thing that I want to tell you about are about these images I have on the left-hand side here. These materials that are changing into all these different shapes, a flower, a little horse or something, and a scary face, and I'll explain what I'm showing there. So what kind of motivates this work is the idea of, you know, robotics has really transformed our world, right, in terms of manufacturing and in other ways. And, you know, they're kind of ubiquitous now, but you can also find all these funny videos without too much difficulty of things robots can't do. Right? Things like stepping over a box, or, you know, following a dog and slipping on a banana peel, or this one's my favorite, trying to chop an Oreo, right? And so the reason these robots are limited is they're actually really intelligent, right? They have computers, powerful computers, controlling them, but they're made out of materials that are not soft like we are, that can't like grip things very easily and just change shape, right? And so there is interest in making soft robots. And these are maybe some of the latest examples. So this is like a little soft robot that can play the piano, right? So now you can start to do things that people can do and animals can do. But really, soft robots are really limited, right? So in this case, they're just powered by compressed air. And this is an active area research, but you know, if you have to have a big tank of compressed air following your robot around, it's also limiting. This is what's called a dielectric elastomer. It's just powered by a very high voltage that deforms a plastic. And so we're interested in maybe coming up with materials that can do better than this. Yeah. Ideally, we'd want to make flubber. I don't know how many of you are familiar with flubber. It's not a very good movie, but it is interesting from a scientific perspective. Like, can you make a material that changes shape like this, that dances? You know, there's other ridiculous things in the movie, like it can fly and do all this crazy stuff. But you know, can we just make a soft material that can dance and change shape in just arbitrary ways, right? And that's actually very hard. And so the materials that we've been working on, they're known as liquid crystal elastomers. So what they are a combination of liquid crystals and polymers. Liquid crystals we all know, even though you may not be familiar with the term. So displays, LCD displays have liquid crystals in them. They are liquid materials. This is a drop of a liquid crystal. But they are also birefringent. They also have these properties that crystals do, because at the molecular level, liquid crystals, they like to kind of organize spontaneously. And in this example, this is a pneumatic liquid crystal. All these molecules like to point in one direction. And so in a liquid crystal elastomer, we take these liquid crystal molecules, we attach them to a polymer, and that's kind of what I show here. And now anything that changes the orientation of a liquid crystal deforms the material, so produces a large shape change. And so liquid crystals are very responsive materials. That's why we use them in displays. Polymers usually are not, but now we couple these two, and now we can get some shape-responsive materials, right? And the kind of, you know, these aren't new materials. We didn't invent them. These, you know, the classic example of a liquid crystal elastomer is shown here. It looks kind of like a rubber band. When you heat it, it contracts. When you cool it, it expands, and it can go back and forth as much as possible, right? But we wanted to do more than this, right? Because we want to make a soft robot. We don't want just something that contracts and expands. We want to make all these different shapes. We want to get to flubber. And I guess our insight here was that liquid crystal elastomers, they're made using two steps. And you know, this is getting a little bit into scientific details, but we first do one reaction where we have all these liquid crystals that are disordered, and then we do a second reaction where they're aligned. And this is a short video that shows how we make them. We don't need the sound here. Oh well. So you take this liquid crystal, it's hazy, it's bright. I have it between crossed polarizers. You stretch it, it becomes dark. That just tells you the liquid crystal molecules are all orienting in the direction that I'm stretching, but it's still birefringent. So if I tilt it at 45 degrees to the cross polars, it's still, you still see light that's transmitted through. Right, and so what I think our most recent work here was to realize that this idea of double network elastomers is kind of a really old idea. So you can go all the way back to the 40s, and people were studying this idea of a first and second network in rubbers. And they had this phenomenon that they called a permanent set, where if you had one reaction, and then the material changed shape, and then another reaction, then the final shape of the material would be somewhere in between. And so we wanted to go between two different shapes, right? So what we realized was that if we want this to happen, we kind of need to balance this first and second reaction. And so I'll show you what happens when we do that, but that was kind of the key concept. And this is an idea of how we did this. So we would take our elastomer, our liquid crystal elastomer. We first make one network. We deform it into some shape. Then we make our second network. And now these two networks are kind of fighting against each other, and we want them to go back and forth. But if we tune it just right so that these two networks are balanced, we can get them to go kind of back and forth completely and seamlessly, right? And that's what we want in soft robotics. This is more details on the chemistry we're using. It's thiolene chemistry. It's actually relatively simple. I'm happy to go into some of the details, but I won't go into the chemistry more than just to show this slide. And this is an example of some of the optimization that we did, where we would take this network and we found, you know, how do we think about optimizing it? We thought about the modulus of the second network relative to the first. So how stiff is that final material relative to the first one that we made? And what is the optimal stiffness? And we found that the optimal stiffness was a value of 4. So once that second network is 4 times different than the first one, then we have a material that's appropriately balanced. And this is actually very recent work that was just published earlier this year. And then once we identified that optimal composition, then the student working on this project, Morgan, just had a lot of fun making a lot of different shapes. She found she could take her liquid crystal elastomer that was initially flat, kind of deform it into whatever she wanted, and now she has a material that goes back and forth between the initial shape and the final shape, right? But that network optimization was key. So she made this thing that curls, goes back and forth. She imprinted this into a Lego just to show you can get a flat sheet that has these features that come up. Embossed rice on them. Of course, we have to acknowledge rice and market rice as much as possible. This is my favorite. She had a flat sheet that will just fold into a flower and then go back. And this is just to show that you don't have to start from a flat sheet. You can start from a non-flat, like a curled kind of cigar shape, and then a final kind of wavy shape, and you can do this as well. And then this was, why are we making a face? Well, there had been a paper published a couple of years ago where they did something similar, but they used a different technique to program their shape. And if you look at their shape, they do capture a face, but their method can't get some of the really broad features like the forehead and the cheeks and things like that. The sharp ones they do great, like the tip of the nose and the rounds around the eyes. But with our method, with our very simple programming method, we're kind of able to capture, all of these features. And so really this was a comparison to what has been done before, but it is actually a really good test of if we're going to take a soft material and we need to capture like very sharp features, very broad features, it's kind of a challenging material to capture. So this is an example of a lot of the different shapes we have. All right, so some of you may be wondering, well, what's the application here, right? This is very far from applications. This is maybe kind of cool, but you're never going to use this for anything. Which is fair, right? And honestly, a lot of the stuff we do, sometimes we don't have an application in mind. So last year, Toyota contacted me out of the blue, and they're interested in trying to improve their cars by, instead of having visual displays and screens that you have to look at to press while driving, which they said is not ideal. It looks pretty, but it doesn't really work well. They want to have a surface that maybe you can feel. So you can feel when a button comes up, then you can press the button, and maybe another set of buttons comes up. And so you don't actually have to take your eye off of the road. You can kind of operate these buttons, so you need some kind of responsive dynamic surface. And so they're potentially interested in working with me to develop a surface kind of like what they sketched out here, where you have something flat. You can have an arbitrary number of buttons come up that give options. This is a flat sheet that we programmed where you have these little peaks that come up and then they go away. We can also make a soft robot. So this is something we did in collaboration with a group at University of Houston, where they took our elastomer and they put a heater that was flexible on it, and they made a little worm that could crawl forward. It could also crawl backward. It can respond to light. And so, I agree it's not a very impressive robot, but it's getting at this idea that we can take our liquid crystal elastomers, if we interface them with some sort of intelligence, some sort of stimulus, we can start to get some robotic functions. So this was their vision for replacing a display with something like that. All right, so that's the first part of my talk. The second part I want to talk to you about is another set of flexible materials. In this case, it's heat. Yeah, but we want to get away from heat, and Toyota does too, because they don't want their surfaces to become really hot when people are operating them. So they're little GIFs. Yeah. So this is actually, and this is actually heating, and then one of the limitations of these is that they also have to cool to go back, and so they are sped up. Yeah. Oh, they can go back. So they're completely reversible, as long as you don't like burn them or damage them in some way. So they're completely reversible. They can go back and forth. It shouldn't, as long as it's. I mean, we haven't tested it, but as long as it's within kind of the temperature range that it operates in, as long as you don't do extreme deformation or anything like it should be fine. Yeah. Yeah, in this case, that's one of the major limitations. It has to get up to about 80 degrees Celsius. Yes, that's to get to the full change shape change. Now we've gotten that down to about 30, but then once you get down to 30, you lose a lot of the shape change. So there's kind of a trade-off here. But yeah, but there's other things. So you can also use light to stimulate them without any heating. So if you put in a light responsive molecule, and that works, except then the shape change is slow. And so then we have to, what we're thinking now is if we can re-optimize that network composition, we can actually speed that up with light. But that's very much an open question right now.
And so it contracts when it heats, right?
It actually, I mean, not necessarily, right? I would say, in this case, well, the way to think about it is we're programming in two shapes. We start with one shape, and then we deform it and go to the next one. So when we heat it, it goes back to the first one. It could stretch. It could do something else, right? Like in this case, when we heat it, it goes into this wavy shape. When we cool it, it curls. It doesn't necessarily just contract, right? It's whatever the first shape is that you programmed. Yeah. So what's happening is the liquid crystal order is decreasing, and that's coupled to a shape change. Potentially, yeah. Except these don't respond to water directly. Although, what's that? With heat, yes. Yeah. So I think a shape like that could definitely be done. Yeah, waves and wrinkles and things like that. Yeah. Yeah. No, and I think that's very doable. Yeah, we can make a little LCE flower that'll open up in sunlight and then close up again. That's a good idea, actually. Yeah, so the ratio is it can go as low as a 4% strain shape change, and that's important so you get these kind of broad features. And the maximum we can do is like 100%, which is doubling its length, for example. So it's that 4 to 100% range for these particular materials. Yeah.
What is the process, if you can explain it in a more like tangible way, like not chemistry, right? The way that you program between those dual networks?
Yeah, I think the easiest is to go back to this video. Right, so this is actually, this material right here is kind of what it looks like after that first step. It's soft, but it still has some reactive groups. So all you have to do is you have to stretch it or press it or twist it or do whatever you want for it to have its second shape, and then you shine UV light on it for about 5 minutes in that shape. Then you fix it. Then you fix that second network. So it's a second, so I'm not showing that part here, but what you do is you make your first one, and then you... Yeah, so what you do there is, in the first step, you have these thiol groups, and they react with the acrylates. It's a base catalyzed reaction. But what we do is we have this so that there's an excess of these acrylate groups. So I kind of show that here in the schematic where you have these acrylate groups hanging around after the first network. And those are UV reactive, right? So you kind of do one reaction that remembers that first shape, and you kind of preserve some functionality, and you deform it, and then those react in the second. And so that's why you have the second network that forms in that second shape. So it really is like two networks, right? And one remembers the second one, remembers the first one. They are competing against each other too.
It's only like in plastics as well. You have one that reacts to a certain input, and then
Yeah. And if you want to see how we make them, we can show you. Yeah, it's actually not too hard at all. Yeah, they're fun materials to play with. And I'm not going to talk about this, but we've also been 3D printing these, right? Because if you can 3D print these, you don't have to start with just a flat sheet. You can start with much more complicated shapes, and so, potentially, yeah.
you need to collaborate with sculptors.
Or we've thought about like coding some shape, and then we kind of fix that, and then so we start with kind of anything we want, and then we can deform it. No, I think that's possible. We haven't done that yet. So So I'm talking a lot. Should I go on? Or? Okay. So a second thing I'm going to tell you about is solar energy. And so I'm also working in a very different area of making what are called organic photovoltaics. So these are solar cells, but they're made from polymers. They're made from plastics. And why do you want to make solar cells from plastics? Well, first of all, they become much cheaper to make. You can literally just print these. Secondly, they're very lightweight and thin and semi-transparent, right? If you buy a silicon solar cell, they're very heavy, they're thick, they're expensive just to install. These can potentially be kind of low-cost portable sources of solar energy, right? And then there's also other applications. Since they're polymers, they're also flexible. And so this isn't our work. This is work from Switzerland, the lab of Gezi. I'm sure I'm not saying that right. But what he demonstrated was he could take some of these polymer solar cells, these polymer photovoltaics, and he can actually implant them in the retina of an animal and use that to treat blindness. Because what he showed was that when light hits these solar cells, that stimulates the retinal nerve, and they can start to detect light or start to detect things. And so this is an application you can never imagine with silicon solar cells, which are hard and heavy and expensive to make. You need the thin film and flexible materials. And so these are just, as a motivation, 2 reasons why we're studying the polymer solar cells. I will say that there's been a lot of work in these polymer solar cells over the past 15 years, but it's only really been in the last 5 years or so that it's been recognized that these polymers aren't as flexible as we need them to be. And so if you stretch a material with a solar cell on it, you'll see very quickly in just a few percent strain, you start to get cracking in the active layer, and that causes the device to fail. This was a field test that was done with these materials, and they said mechanical failure was the biggest problem, why they lost power. And so we've been thinking of ways, this goes into the photovoltaic process in the solar cells. I'm happy to say more about that, but I'll just skip to this, and I'll just say that in these organic solar cells, you have 2 types of semiconductors, a donor and an acceptor, and that's what I'm showing schematically here. You can have an interpenetrating mesh of donor and acceptor. And then what we did to make these flexible is we added a 3rd component. Now we added this kind of flexible mesh that kind of holds everything together, right? And so, yeah, this is a video that shows, these are very thin. These are about 100 nanometers thin. And so this is like a pure layer. You can see how fragile it is. We just tap it, and it kind of just breaks away. And this is kind of one of our active layers where now we have that mesh in there. And you can see now it's more like a film that kind of can sustain more of a deformation, right? And so that's just a proof of principle, really, but we can actually go through and measure, all right, as we add more of our mesh, it's again using this thiolene chemistry, when does the material crack? Without any mesh, it cracks at 6% strain. As we add 10% of our thiolene, we kind of push that limit out to 16% strain, so we can now stretch it up to about 16%. When we add 20% of our thiolene, we get about 25%. So basically, more and more of this mesh we're adding, the more flexible the material is becoming. And so from a mechanical perspective, it's working. I guess I left out details here. The other question is, as we're adding this, does the device still work? Because you'd imagine that as you add more and more of this flexible mesh, eventually you're not absorbing light, you're not separating charges, you're not conducting electricity. So we found the optimal was at about 20%, where we still can get good performance and we get flexibility. And this was our proof of principle where we actually made flexible photovoltaic devices. This goes into the multi-layer device structure, and we show that we can actually make this, and we can stretch this device, and it works even as we're stretching it. It does fail to some extent, but in black is kind of like the unstabilized material. It fails very quickly, whereas as we add more and more of this thiolene, we get better, more flexibility. And so, so I think this can be potentially a general solution. It's a very simple additive in one layer of your photovoltaic device to just improve mechanical flexibility. And so we're working now on getting higher performance devices, so trying to just push up the currents and efficiencies that we can achieve. And I'll just go to the last piece very quickly. The last one is shown kind of on this cover image. It's basically the idea that if you paint something on a surface, sometimes you'll paint kind of a mixture of things, right? Paint really has several different components. And what we want to do sometimes is drive one of those to the surface, because you want the surface to, for example, be self-cleaning or super hydrophobic or super hydrophilic, depending on the application. And so this is just one slide motivating this idea that all plastics have some kind of additives, and they're essential to the function. And what we're doing is we're making these polymers that are called bottle brush polymers because they are shaped like bottle brushes. They have these kind of very short, if you look at the schematic here, this is a bottle brush, or this is a bottle brush. It has these kind of short polymer bristles coming out from one like long stem or one backbone. And what we found is if we make these bottle brushes and we mix them or coat them or deposit them, they always want to go up to the top surface. We can mix them with a variety of polymers and materials. And so, yeah, so this is, on the right is an actual experimental data showing where these bottle brushes go and how they go to the surface in red in your bulk polymer. And so I'm happy to say more about that. I know I went through that very quickly. I do want to acknowledge kind of funding. These were the students that worked on the LCE part. Morgan Barnes is a PhD student. Sueda is an undergrad at Rice, and Sean is actually a high school student that worked in my lab this past summer from Dulles, the same school I went to. And this is the rest of the group. Yilin and Jichi were working on the photovoltaics, and Roy has been working on these bottle brushes. So I think I'll stop there, and I'm happy to take any other questions you may have.
We're going to have a Q&A.
Okay, great. Thank you.
Hello to everybody. I am Geraldine Interiano Wise. It is really courageous of me to be here after Rafael. Super courageous, but you know what? Salvadorians are resilient, and here I am. Thank you to Laser, to the leadership at Laser for doing this. I am inhabiting this world that of art and science, and in awe every day of the possibilities. And I hope that you leave today in that awe of where are we going, because we're going somewhere. Just like John was saying, we're going somewhere. And who's pushing and how far are we pushing, that's up to us. So thank you for going for the ride with me. I called this talk the Accidental Immigrant and the Nahual Project. It will be self-explanatory in some of the videos that I will show, or perhaps it will explain a little bit more. But the accidental immigrant has to do with the fact that I've wondered why this internal push to new frontiers. And to me, the new frontier is the brain. And I dreamed of being an astronaut when I was little. And it was readily apparent to me that there was not going to be a girl Salvadorian astronaut anytime in that program. So but I also love the idea of frontiers. So I came to the United States to study. My parents had said all along, you're going to go there. That was that educational frontier. And I did. And but I didn't come to stay. And that's why I'm the accidental immigrant. And what happened was the Civil War. And the Civil War touched everyone in my country, and indelibly. My children at times have said, "Oh, mother, what an easy life you've had." And I think, again, what is wrong with that statement? And it's the fact that they have no idea that it broke my family and it broke an entire country. And you wonder why I have to do art. Because when you're touched that way by movements of humanity, you have to have a platform. And it wasn't going to be writing. It was going to be art. So that the fact that I'm an immigrant is accidental, but I am a very grateful immigrant. My beginnings, actually in art, were in El Salvador, under the tutelage of Violeta Bonilla, who on the right you can see, she was a muralist. On the left you can see one of the biggest monuments that she did in El Salvador that we call El Chulong, which means the naked guy. And at the time, I was probably 8 years old when my mother, who is in the audience today, first heard that there was a really good artist that had come back from Mexico under Diego Rivera. And I think Geraldine has some potential, so let's put her under her. Well, every Saturday in the volcano, that's the San Salvador volcano where we live, and every Saturday, my mother deposited me at the mentorship of Violeta Bonilla. And I did not know as a child that that would be changing my life. And the stories of Diego and the rumors about Diego and then about Frida, and it's like that was a part of my every Saturday. And it wouldn't become absolutely ridiculous until I left there. But she was a fabulous artist. And I want to tell you about El Chulong, which still resonates with me, and it's one of the things that Surpik, who has been very kind as to be a great sounding board and encourager to me, we talk about authenticity, and authenticity matters. This Chulong is made out of stones out of the 14 departments in which El Salvador is divided into. So she went looking from every department to natural stones in the different colors, because she wanted to represent every last human, which is what Diego did with it's one of the groundbreaking thinking in art that happened with the Mexican muralist. She came from there. And so what does she do? She does this beautiful chulong, which was the laughing stock of every child. But I sit here in complete awe that was a master thinker, and she was my mentor. I could only dream of being as good as she is, or as authentic as she is, but I needed to show you that. And there she is with Master Diego and some white guy. And so the very early, I did the rigorous thinking, all in oil, mix your own grays, mix your own everything. So I did it. These are still in my house, and I still don't know what to do with them. And then came the war, and then I saw my people with a different eye, and then art would change forever, because I knew that I just was carrying my people in my DNA and connecting to them. So about connection. If I was connected to my people, and my people are connected to the Maya, but the Maya came from the Native Americans, and the Native Americans came from over there, so there I am in the path of always researching. I am probably the #1 person in researching what is the latest anthropologists are talking about in the beginning of humans. And I needed to tell you about this. This is El Castillo in Spain, which was supposed to be one of the oldest hand stencils on Earth, but it turns out that the Sulawesi cave ones are about 1,000 years older. Sulawesi in Indonesia. So now imagine, we thought Eurocentric because African man had moved to Europe. We thought it was Eurocentric, and here we are. We are literally our living history. And I think that's a really exciting thing to think about, that we are living history, that my art is living history, that our art is living history. So the Sulawesi caves, and this is the picture that I wanted to show you, because because of the scale of those hands. And that's a incredibly, do you see the hands? They're little bitty hands. And what that is telling them, it's a different homo. So if the Homo sapiens are coming out of Africa, then this is a different homo altogether. And yet this need to do art is embedded in their DNA. And if that's not the most exciting thing you're going to take out of here, I don't know what is. That basically, and the latest thinking about that is that it's embedded in us as those beings that would become who we are. It's that innate. So what does that tell you about art and the brain? It's that we are meant to be creative, that our brain is at our best when we create. And everything you saw right now out of Rafael is creation. And that is one brilliant mind. But I do believe that we are at our best when we create. So about beginnings then. So where do I take a turn? Where does everything that I'm doing now begin? Because I am about those beginnings. And it was a chance encounter at the, probably at this point about 7 years ago, at the retrospective of Rauschenberg at MoMA. And across, there were enormous paintings I had never encountered, and across the room I said, that's a painting that I could have done. And of course I was attracted, and when I came to it, it was the time paintings. If you don't know about his time paintings, it's a genius of him, because if you think about the fact that abstract expressionism was a breaking of the rules, and it was really about the physicality of the material, but the physicality of the person moving the material. So he decided that, well, in this case, I'm the one painting. So I can do these time paintings. He set up an hour clock, the little bitty clock, which is in there. It's in there on the left, on the right. He set up an hour clock, and he then turned it away from the audience, because the audience then saw him paint. Because, by the way, isn't that like the ultimate abstraction? To see the body moving that paint. And that's what he did. And I thought that was absolutely brilliant. But then I researched further into, so what else did he do in this new thinking? Well, he collaborated with Trisha Brown. Trisha Brown, one of the groundbreaking choreographers in the history of modern art. 1983, did you tell me, Serpic, that you were in New York? 1983? 1983, somebody I know said, I could have sworn it was you, said, I was at that dance. When she broke ground with a dance by the name of Set and Reset, and if you look it up into YouTube, I would love for you to do that, because it is really what enabled me to know that as an artist, I can prepare. I can see what spontaneity looks like, because that's what creativity is. I can take spontaneity, but I can repeat it. That's what she did. She actually did that looking at the bodily movements of her people, of her dancers, preparing for her choreography. When she realized that the real choreography is them, the authenticity of their movement when they are stretching was brutally honest. It's about the body. It's about every knuckle and every joint in the body. And then she said, I can take that and I can choreograph it. I can repeat it. And that's Set and Reset. And it broke ground. Well, when I hear her, it's in YouTube, she's talking about this, I thought, but that's exactly what I can do with art. So that's what set me then into this Horizonte, I'm sorry. There it is. Performance. That's the real music. So I am performing to music live. The music is by Annie Gosfield, one of the top contemporary classical composers of our time. She's out of New York. She's my age. And this woman is her music is being included in music festivals around the world in the mashups by the famous DJs. That is how cool this woman is. And this particular piece of music moved me the minute that we were working in collaboration with Musica. And they sent me all these pieces, and I kept thinking, that's a black painting. That's not even a painting. That music doesn't even move me. That doesn't talk to me. And then this one comes about, and I was at the edge of my seat with this music. Well, I was able to talk to her when she heard that I was putting art to her music. We were able to connect. And this music, she researched about the codes that were used by the resistance in World War II to move humanity. And that's that music. Well, by then I had already developed my coding on the spiritual and the visual and the nomenclature of the Maya people. And it was so beautiful that here I was bringing my codes to her musical codes. And Serpig happened to be in the audience that night. I don't know if anybody else here was in the audience, but it was a breakthrough for me for sure that I could prepare to that. That 17-minute performance took me 6 months of rehearsal, of thinking, of researching. I researched the 5 pigments that would be available to mankind 70, 80, 40, 30,000 years ago everywhere in the world, and the palette is out of those 5 pigments. And I sourced then the indigo pigment out of the ancient seed plant in El Salvador, just to lend authenticity to the painting, to the process, to the meaning. And it was made as an ode to my Salvadoran people. So I don't know if you noticed that I used all very rudimentary tools to make art in a very in a theater environment, but as an ode to my people who are the cleaning people of this country, who are the workers, and who are transparent, but that they have a voice, and I am one of those voices, and I'm very proud of being that. So this one, I want to tell you about the fact that in between all of that, there's art. And art happens for me because it is a platform for many things that I need to say. I'm not sure if people are listening, but I need to say it, and that's really what matters. And in this case, if you remember the time when we were at a fever pitch with Black Lives Matter, and it's not about the Black Lives Matter, it's about the fact that we were killing young black people. And I just kept thinking, if I was one of those mothers, I would be louder than them. And I needed to understand that because it was taking all our airspace. Do you remember? It was taking our oxygen because together we couldn't breathe, and yet we couldn't change anything. Well, that's when I went then, again, digging into the beginning, going into the authenticity. What unites me with those mothers? And I went digging into, where does white skin come from? And scientist out of Duke, 2006, finds the genetic aberration that leads to white skin. And it has a name, it has a number, the genetic aberration. And I was just so moved by the fact that I got to know that, but then the world needs to know that, because I could then move away from my biases and understand the connections, the human connections, because that's what art can do. It is a platform for deep understanding, deep connections. And in this case, this is my body of work that I called One. And it came out of this little sculpture that I made in two-tone wood that I had the radio on in my studio, and I heard one more killing. And I'm going to start crying. But I had to do something. And I went to the tools, and I did that sculpture. I didn't stop until I finished it. I didn't know where it was coming from, but I understood it. And from there came these other small paintings on paper that really are about the fact that we're coming out of the pain of those people. We are Africa man. And there's no difference between me and them. And I was able to really reach far in my understanding through my art. It is also a platform for me for understanding the beautiful relationship we have with the planet, but that is so broken. And my latest understanding about that just happened in May when we went to New Zealand for the first time. And people had said all along that you need to go to New Zealand, and everybody here should go to New Zealand, but nobody had told me why. Every one of us is going to have our own interpretation of why we should be in New Zealand. Well, I found mine. I found it at the museum in the island where they signed the treaties with the English, and it had to do with the Maori word for nature. They used the same word as placenta. And I haven't done the paintings on that yet because I have been too busy. But I will, because I think that that is just about the most beautiful way to look at how we need to look at nature, about that nature that nurtures us and gives us life. And so this in particular, this body of work is about the Conacasta tree. It's called the Plight of the Conacasta. And the Conacasta tree is a environment and game changer and life changer. It is a gigantic species of tree in El Salvador that is native in El Salvador. And they are poaching them and they're so big, they're like gentle giants. And so they lie them by the edge of the road and then they cut them up. And I thought, well, but maybe these people need to make a living. But then I stopped by the end of the road. I said, tell me about this tree. Where was it? Oh, we just found it, and that's not true. And so I said, well, how much is that piece of that tree? It was the most giant piece of tree you've ever seen. Well, if you give me $300, I'll put it in a container for you. $300. I thought, that's what this is worth? And at the end, I said, no, I cannot take a piece of that. But there was a piece down in the floor, just a really, I think you see it actually there. You see it as a shadow. There's a shadow there. That's that piece, that's the shape of that piece. And I took it with me, and I said, will you sell me this? And he said, yeah, give me $10 for that. And I thought, you idiot. But I didn't have $10 with me, and so I was asking my brother, could you lend me some money I just needed to take this feeling with me. And at the end, the guy said, oh, just take it. So I took it, and I developed this. And this is, to me, hope. This is the hope. This is a river of life, as far as I'm concerned, what you see there. And to me, this is about the hope that in this river of life, that what we do wrong to the environment can actually become part of the healing, and that we can come out somewhere else. In this case, the art is the platform to talk about my people. And I was talking to Rafael, and the fact that Rafael has 2 children. And I was telling him, in no uncertain terms, those 2 children are part of the new Houston. And they're the part of the new country, the part of the new world. Well, and so many new Salvadoran immigrants are going to be a part of this country. And I say, well, let me talk to you about this incredible intellectual patrimony that the Maya have left behind. They were so smart, they knew so much, they dug so deep. It's absolutely beautiful. I don't have to go anywhere else. It is all there for me. And this particular series, I call it the Infinity Series, because it has to do with the way they count infinitely forward and infinitely backward of creation. They have a moment of creation, and they are connected infinitely. And that's just such an enormous abstract thought. It's as big as the Sulawesi cave thinking of the hand. That what I didn't explain then was that it is the thought behind that hand is that it's such abstract thinking that was already man, that no animal could do that abstract thinking. Well, here are the Maya, and they're doing some incredible time-space thinking. And I keep up with science as well, and so I just had to do the series in which this is a representative of, in digital form, of the way that they bundled numbers in order to be able to count by hand infinitely, forward and backwards. And the idea is that this becomes an installation, which I already have done one, and that I actually bring it to Hispanic people. So I can open the door to that thinking. You have my DNA. You have the Maya DNA. You have this inside of you. You just have to do the right thing and connect. But connection is really what all this is about. And then the other platform is for going into the brain, which I have told you that is my last frontier. And so this is a series of monoprints and etchings that I'm doing at the Print Palace at Rice University under Karen Broker, and exploring those very ephemeral thoughts and ephemeral feelings that we can think reside in the brain, but really they are what connects us all. And so they reside somewhere else, which is one of the reasons I can very easily put them into monoprints, because once I put them there, I feel like part of my thinking has been cast. And then this is another set, and it's the middle one that I want to tell you about, which is because of technology, we now are able to see the baby brain without having to do it post-mortem. We can see it at birth. Well, in a scientific symposium in California, I encountered the scientist that is looking at the connections of the brain at birth, then at 6 years old, and then at 14 years old. And this one in the middle is the baby brain at birth. And what struck me, this is my monoprint, needless to say, an etching. It's an etching on a monoprint. And what struck me was the incredible responsibility, number one, of parents, and number two, of humanity. It is our responsibility that our children, that our Houston children, that our Texas children, that our American children, that our Salvadorian children, that our world children fill up that brain, because those connections lead to a better brain for all. And that is really a deep thought. And so I needed to make that. I did that particular series for a fundraiser for the Home for Cerebral Palsy Children in El Salvador that my mother funded. And so all that money got sent to the children, because those brains are the ones that need healing. So then that leads me to the Nahual project, which I will explain the Nahual. Nahual is a Maya term for the spirit that in their mythology or in their thinking, there is a spirit that is assigned at birth to each person. And they call it a mirror spirit. And I was able to get my Nahual read. It is read by the shamans in the Maya world. And by golly, if she didn't describe me, the artist, and she had no idea who I was. She described the colors. She describes the shapes. She describes what moves me. She describes how to heal me. She describes what's wrong with me. And I was just blown away. There's just something true to the fact that maybe she could read my aura. I don't know. I still don't know. But I am enthralled with the fact that this Maya world was just so deeply knowledgeable. So when Dr. Jose Contreras Vidal, who is the head of the Brain Center at UH and Cullen Distinguished Professor in Electrical Engineering, and when he came to me and said, I am studying the brain, but I need the brain on art, because that's the higher brain. So since you're doing the live painting performance, can we do the EEG, so mobile device learning of the brain? And we developed it at UH and my studio, and we took it to the conference on the International Conference on Graphonomics and the Brain on Art in Cancun in June. So this is my team, Jose in the middle, and Eric Todd, one of his students at the lab, who then developed the algorithms with me to be able to then take my brain waves as I'm painting and develop the Nahual, which is the digital mirror painting that is coming out of my brainwaves in real life. So stroke by stroke, it is happening at the same time. I want to show you, if you will indulge me with these 3 minutes, of what I got out of that conference. There was all scientists. There were a few artists, including Dario Robleto was there. And, but I thought what was in the minds of the scientists was really beautiful. And that has moved me to go further into the science, understanding that scientists are actually hungry to understand the creativity part of the brain. So, let's see. So I wanted to show you what came out of that conference. So first of all, that these scientists were needing to know where art, empathy, brain, chemistry, spirit, humanity, like how do we do all this? This is in the hearts of scientists. And I think we have to get into each other's space in order to further that. And this is the painting that I did. So here is the painting, the physical painting. There, I extracted the Nahual, so the generative digital painting, and then this is when they come together. And so, the conversation with Dr. Jose Contreras Vidal went back and forth into, well, where do they reside? Well, it's sort of like, where does the spirit reside? Well, they reside together. And the exciting thing about that moment, the aha moment, is that when they reside together, there is 20 minutes of a painting that is changing. And that is about the most exciting thing to me, that there is a painting that I'm creating, a digital painting, but that it's changing for 20 minutes. It's like a new permutation of art, and I... The digital output. Mhm. Right, right, right. So you...
Manipulated, or is it like, or what are the parameters for that image? Like, what is, like, is that purple is a certain brainwave?
Yes, that is, let me see if, here, no, just a sec, here, right here, right here. So this is the algorithm with which we're working, and all those diagonal lines are the input of the brain in real time during the creative process. And so as you see there, you see that they're almost separated into three different inputs, and there's several things that we're doing. One of them is shapes. So the generative shapes, we have a circle, we have a rectangle, and we have a sphere. That's the beginning of the shapes, and then depending on what part of the brain we're feeding into them, then they become different shapes. So you see, you didn't see circles there, but that's the beginning of that shape, so it's generating that way. The other thing that we're doing is, and I'll show you, I think it's here. It's here. The other thing we're doing is, because if you think about it, I'm an artist, and the number one thing that came out was, well, that thing doesn't look like anything I would even think about. That's not good enough. So then I had to sit down, and I'm not an algorithm person, but I sat down with Eric, and I said, okay, let's choose those colors, let's choose those shapes, let's choose light. And so I brought my total creative, what are the tools that I have, and I brought them into the digital space. I couldn't manipulate it if you killed me, but I brought the same tools, which really goes to show you that this confluence of art and science is real. We can help each other. So in the end, these are the tonalities and nuance. I mean, it took us forever to get there, so that the painting could come out as perhaps not a mirror, but as something that talks to me, because it needed to be my art, not just a computer art. Does that answer it?
That's data visualization.
Mm-hmm.
That's kind of like a genre. So what I find interesting is that you're kind of visualizing what you're talking
Yes.
about, and then they're taking that data and re-visualizing it. But
Yes.
these parameters, it's difficult. I mean, as data visualization, I think it's important to understand the parameters. You know, they're part of the artwork. You know, the data is
Totally agree.
not just totally abstracted, because I mean, you could make it have pictures of cats and dogs.
Exactly. Exactly. You can do anything, and that's what you're saying. But then what is it that would be appropriate to then live on my painting as my Nahual? So this is what I want to show you now is a session, and you'll be able to see more about those colors that I did in my studio, because we're developing further that concept. So just a second.
What's inspiring you? What were you visualizing? Did you come with a plan, or you just thought, is it like performative and I guess
That's a really good question.
improvisation?
That question was asked by a scientist, because remember, we were in a conference, and they had all put forth scientific experiments and findings about measuring creativity. Where is creativity? How do we hone into creativity? How do we teach creativity? So all these things had been presented, but they had never seen somebody create live. So they wouldn't even let me leave, because they all of a sudden knew that they had been thinking something, but maybe the reality is other. Now, to be fair, remember I told you about Trisha Brown. So I made, anytime you go into your studio, and Terrell would know this, anytime you go into your studio, you're making a million decisions without even thinking. Like, which bottle do I put here? That's already a decision, because guess what? When I'm just thinking, okay, I need something, and I'll just grab this and do it, well, by putting the bottle there, I already made a subconscious decision. So we're making subconscious decisions all the time. What I did is I took anything that I thought could be closer to the seat of the Maya in the lowlands of the Yucatan. And that is what I took. So I didn't take what I put in my studio. Now I was going to the seat of the Maya. I was going to connect through those incredible waters, those colored waters. So that is a unique painting. Now, had I rehearsed? Did I know what I was going to do? Yes, I took a bunch of those Maya loom materials. And so did I know that? Yes. Did I put a bunch of things? Yes, I chose those others. So did I know what tools? I had already rehearsed with the tools. So there was a lot of parameters I had already set. But was that unique? And let me tell you what I didn't tell you. And I think if I can make this work, I think I can do this. There. Those are my brain waves sonified. So that's my auditory input, is my brain. That's the Nahual. So you see the generation. Yes, I am. I'm going to give you an analogy, and I just want you to see the generative marks there. And so that was already the very nuanced colors that then we came in and was able to then get. So that's just a little piece of that generative. And these are mark by mark. So what I'm marking, this is marking. So is it distracting? It was intensely telling me something, and I'm still trying to figure out what it's telling me, but I feel very much like it's regenerative. It's almost like I'm in a loop. It's super intense experience. And by the way, what you saw in my head were not rollers. That is my mobile EEG device. So this thing is digging into me, and then this sound of my brain, and it just feels like you've just got to keep going, and you've got to keep going. And so it's interesting that I have to kind of calm down my creative, not just react to that, but then put it into my, let's call it my nomenclature, so that I can produce a real painting as opposed to just reacting to these shrieky things.
But did you figure out how to produce silence?
I am actually working on that. I'm actually working on that. And that, say that again? You can program it. Like I could program, yes. You can program anything. But the fact is that the idea here is that you learn to then super concentrate. Like get into an alpha, that you're in a zone. And the truth is that I hear it, it's like a buzzing, but on the other hand, when I am in the zone, I don't hear it. So I don't know, I have yet to figure out when I'm in this, I have to look at the video, how it correlates to the sound, in order to remember when I was in the zone to know what that was about. So let me tell you, this has many, many facets to it, that it's very complicated, and we're just touching the very tip of the iceberg on all of this. So you saw the algorithms and you saw the colors, and then that is the result of that particular Nahual, the one you saw me painting in the studio. And you see, it's the same painting behind. It's just that there's iterations of it. Yes, Eric is the only guy that he's at the computer, but I am.
Have you tried doing it like yourself? Do you, I almost feel like
No.
it's a change if it's a performance versus a painting that you're doing.
Well, did you see me? That was in the studio.
Yeah.
So yeah, I am a.
Yourself, I don't know what you're doing.
I know what you mean, and I think that that's another iteration. I think you're right. I think you're absolutely right. There's, this is like a scientific experiment. You're testing some parameters, and then you are saying, well, but I'm not getting the information I want out of this, so I'm going to add this, so I'm going to tweak that. So we are definitely in that process. So this is Dr. Contreras Vidal, and he presented at the Latino Art Now conference that came to Houston with me, and this is what he has to say about why are we doing this? Why is it necessary? And what about engaging the brain and mind towards learning and innovation? Could we teach how to innovate? Well, I happen to know that the Dean of Engineering at Rice is trying to put every engineer through art, because that's where the real confluence of new ideas is going to happen. So we know that that's the case. So then what, could these lead to new aesthetic problem solving? Just like we were talking about Rafael, right? Could artists help you then create something that would have been different than just the scientist at that? So I think that's a really important thing to ask. And then how can we promote social understanding and cognition and advance education and teach better and I think what at the core of all this is, how do we get creativity to bring us to the best of our brain? I think that's at the core of all this. So I want to tell you that art takes a village, and my parents are here, and I thank them for all those Saturdays that I went kicking and screaming. And I got what I needed to get. And professors and mentors, and Scott, my husband, who thought he was diving, but my God, he never thought he was going to dive this deep. And my children, who are courageous, and my Rice community that continues to enrich me. Fellow artists that teach me, John today, teaching me new things. I love that we can talk about art and do that. And then, Tony Brandt, who gave me the chance of doing Horizonte in the performance that was kind of breakthrough for me to how to to be able to repeat and to do this live, which then led, of course, to being able to do it with a mobile EEG device. And then Serpic, who has been here all along, and then Dr. Walter Woodrig, a professor of ours who just recently died, who gave me the chance of going to the archaeological dig in Rome, which was about, again, that connection through space and time, authenticity, understanding where we come from. That came very early, and that was an incredible experience for me. And then my professors who continue to do that now at Rice. So I just want to tell you that I am, the New American Festival is coming to Houston out of New York. They're doing it in different cities, and I am going to be doing the Nahual live. So I'm preparing for that permutation with the new algorithms, et cetera. And then I'm in different things, and I will be performing the Nahual project live at the Glacial as well, under an all Latin American women artists who, did I see Gabby here? Gabby here? Yep. One of my fellow artists is here from the group Latin American Women Artists in Houston, and so they're giving me a chance to do that. And then for 2020, they accepted my live performance with the EEG and a talk about the confluence of science and art at the Texas Association of Museums conference. That's going to be in College Station in April, and I'm taking this to San Miguel de Allende, and then I'm with talks with the Museum of Modern Art in El Salvador, which is right next to El Chulón, right next to. So it's like coming home. It is just absolutely beautiful. But That's what art does. It's like this magical ring that we live in. And then, this artist needs representation. And here's my information if anybody needs to reach me for any reason whatsoever. And thank you for being a great audience. So Eisen, do we want Rafael back here?
Thank you. That's great to be here, for sure. Sure. I'm sorry, what was the question? Do you improve your investigation and research using your students' creativity? Absolutely. Yeah, absolutely, yeah. It's certainly not, yeah, I mean, I guess the way it works is, it's not like I'm saying, hey, go do this, and they do exactly what I say and they come back. It's really more of a collaboration, right? It's like, I think we should kind of, make these materials this way, and then they'll say, oh, that's an interesting idea, but they'll have their own ideas. It's really more a collaboration, not me saying, hey, go do this, go do that, go do that. Because if I did do that, it would not be as good, for sure. We would not get as far or do as much, that's for sure. Right? It's certainly like, yeah, they're learning from me, and I'm learning from them, and I think that's how we really advance the field.
So my question was, both of the presentations were really so interesting, but mainly I had a question since the beginning about the plastic and how this work enters in the recycling conversation and how for the environment at the long term it goes. That was my question.
Yeah, no, that's a big issue, right? And I think people are recognizing that plastics, they last a long time, and they get in the environment, and then they're hard to get rid of, and they cause a lot of problems. And so there is a whole other, I don't have work in this area, but there is a whole field of research where people are trying to develop renewable, degradable polymers. So they're trying to make all the materials we can make right now using natural sources, cellulose, plant-based materials that just naturally will degrade and won't contaminate. The problem is usually when you do that, if you replace some, petrochemical or some plastic with a naturally occurring one, usually you suffer a little bit in terms of the quality, strength, properties, and things like this. But yes, there's a lot of people that are trying to reproduce all of these properties and all these materials with polymers that are degradable. And it's a challenge, but it can be done.
Yes, but also my question was, even if you don't go to other materials, but with these ones, like how in the process of the plastics, how can you, can you do these from recycling used ones or not?
Oh, can these materials be recycled?
Exactly. Can they start, for example, for the plastic people, buy in the supermarket for their groceries, and then could we work those plastic to make, the difference, or?
It really depends on the application, right? So it really depends. Like if you need something that just, let's say, changes shape in one way, and as long as that function works and you just need to clean it off and reuse it, that's fine, right? So that's possible. There's other areas, I was telling Geraldine before the talk, people are interested in these materials for medical applications, for helping with surgery. So if you implant these in the body and take them out, you probably don't want to put them in somebody else, right? And so in that sense, they wouldn't be recyclable. And in terms of the chemistry, at least the materials I presented, you get one shot and you can't redo it unless you kind of break the whole material down, right?
That makes these so valuable if you really get into the stage forward so that you can have like a plastic bag, please.
I think you could figure out the chemistry so that you take one shape and then you can program it to do different things. You can maybe erase it and then start over.
It could be like the yak.
Yeah. Yeah, so I think it's possible, yeah, in terms of thinking about the chemistry and things like that.
I think what is so evident by what you heard tonight is that the possibilities are really endless, and it's only up to our creativity to ask those questions. I mean, how many questions? I've always thought that some of the people that I admire the most are the ones that are able to formulate the right question.
Oh, yeah,
Formulating the questions is the hard one. And even in where are you going? I love that one, right? I love the thought that every one of us is going to buy a pound of something and then put the plate on the thing, or make it a glass, or take it to the supermarket. I love that. So keep working.
Yeah, no, absolutely. It's a big challenge, but yeah, I think it's.
But it's work, and we're doing it now. I mean, we are doing recycling and reprinting with pellets, and it's really exciting. But I had a question really for you about your images that you're getting off your brain, and I thought that you were showing, I think, one on the right side of the three panels, where it was kind of these color representations of what's coming off of your brain. And
Yes. So
they look digital, like they were being printed from a computer.
they are generative, digital. So definitely, they are computer made marks. And so one of the things that we had to do was, when I saw at first what came out, it was my partner, Eric, who was doing the algorithms, it was his hand. And I realized very quickly, and that's it's a really good sign of collaboration, that really, you just can't let things be. Collaboration needs collaboration. I have to get in there, into the weeds, and to show me the sliding scale of the pinks. Why is this so pink? Show me why is this spiral? I don't do a spiral in my life. It's not even exist in my brain. So get the spirals out of here. So it was it's generative, so it's computer generated, but it's not. It is only generated by the real-time input of my brainwaves while I'm doing work.
So I guess what I was really trying to get at is interesting. I mean, have you thought about in terms of a body of work where you actually just allow that to be? So instead of taking that information and then interpreting it back into the painting, saying, oh, I mean, I'm separating into a whole other way of thinking, or
Let me
it
tell you.
is what it is.
Let me tell you what that is. You're talking about AI, and that's where we're headed. But the truth is that if you think about what is the natural progression, just like we gave you a lot of ideas to work on.
Yeah.
The natural progression is on is there the work is, or where is it going? The natural progression about getting to know my brain on art, your brain on art, and every one of your brain on art is the idea that art is not coming out of our arm. It's not that Picasso just repeated that form. It's a neural pathway. And so if you think about the fact that our you have a neural signature pathway of creativity. And so we are headed into that dimension where machine learning can learn through analyzing my body of work what is my neural pathway. Interesting that you say that, because I did the last live painting presentation was last Thursday for the UH Immigration Law Center. And I did a collaboration with Karina Gonzalez, the prima ballerina of the Houston Ballet, and the Houston Grand Opera baritone. And right there at the rehearsals, I told them, I need you to feed me. This is not just we're appearing together. And so when we were going through the rehearsal, I didn't want to get dirty. So I went literally with my eyes closed. I went into almost like you see the athletes rehearse, the downhill skiers that are doing that. I did that. I did it right there. It was the first time I've done that. I think that's what you're talking about.
Yeah.
It's like paint it.
And what happened?
Paint it. Well, nobody recorded it, right? So my point is, but I got it because I understood what I would be doing
Okay.
with that,
But I think it would be interesting to see what, you know.
what the digital output would be of that. Yes, that's exactly right. Yeah, but the other, so one thing is looking at the body of work and have the machine then learn my way with it. But the other one is to actually wear one of those caps, record my EEG for a year in my studio, and put that through the machine, right? So it learns my thinking. So it learns my work and it learns my thinking. Now you put these two together, I could generate digital paintings that come from my brain. AI Geraldine. So this is where we're going. John, we're not far from that. Well, let me tell you why she's absolutely right. Because some of we're measuring 20 centers of the brain, and some of them are associated with movement. As I move the head, it records something different. So actually, you are 1,000% right. It's not just like I'm going to sit here and ooze brainwaves. It's that the movement has to do with that too. So this is all connected.
I hope that this is the conversation here because people want to leave and